Ever wonder how a computer could debate or evaluate an argument like a human? Like, how does it decide if a medical recommendation is trustworthy or if a social media post is biased? Today, we're diving into a mind-bending field of AI called computational argumentation, and a breakthrough that's changing how machines weigh the strength of ideas. Let's break it down. Let's start with assumption-based argumentation, or ABA. Think of it like a legal courtroom. You've got claims, assumptions, evidence, rules, and arguments that either support or attack those claims. For example, if someone says, "Let's go for a picnic," another might counter, "But the weather forecast says rain," that's an attack. Traditionally, ABA systems classify assumptions as accepted, rejected, or undefined, like a simple yes-no. But here's the problem. Real-world reasoning isn't so black and white. What if we could assign weights to these assumptions, like a scale from 0 to 10, to show how strong or credible they are? That's where gradual semantics come in. Instead of a strict yes-no, imagine a dial that measures how acceptable an argument is. A high score means it's strongly supported, while a low score suggests it's weak. This lets AI handle nuanced scenarios, like weighing conflicting evidence or updating conclusions as new info comes in. But here's the catch. Existing gradual methods didn't work well for ABA's complex, layered reasoning. They were designed for simpler systems, not the tangled web of assumptions ABA handles. So, researchers at Imperial College London rolled up their sleeves and created a new approach. They used bipolar set-based argumentation frameworks, BSAFs, to model ABA's structure. Think of BSAFs as a map of how assumptions attack or support each other. By assigning weights to these interactions, they calculated a dialectical strength for each assumption, essentially, how convincing it is in the grand scheme of the argument. To test their idea, they ran experiments with synthetic ABA frameworks. The results? Their method converged, reached stable answers in 90% of cases, beating traditional methods by 20%. This means it's more reliable, especially in real-world scenarios where assumptions have varying credibility. Imagine a doctor weighing evidence from multiple sources, or an AI analyzing social media posts for bias. This tech could make those systems way more accurate. So next time you see an AI making a recommendation or analyzing an argument, remember, it might be using these cutting-edge techniques to balance the scales of reason. Thanks for watching. Drop a comment below if you'd like to see how this applies to real-world AI systems like chatbots or decision-making tools. Stay curious, and I'll catch you in the next video. Ever wondered how AI systems figure out the best answers when there's a lot of conflicting information? Today, we're diving into a fascinating study that compares two methods, DF-AD and QE, under different frameworks called BSAF and BAF. Let's break down what makes one more reliable than the other, especially as problems get complicated. Imagine you're solving a puzzle with thousands of pieces. Some fit easily, but others clash or take forever to sort out. This study is like testing two different strategies for solving these puzzles. The researchers looked at three key factors: how many assumptions the system had to juggle, how many rules it followed, and how complex each rule was. They also tested two starting points for their calculations. Think of them as different ways to kick off the puzzle-solving process. First up, BSAF. Here's the takeaway: DF-AD, one of the methods, was a rock star. In 90% to 100% of cases, it nailed the solution, usually in 25 to 35 steps. QE. It was all over the map. With some setups, it barely worked, but with others, it was almost as good as DF-AD. But here's the catch. As the puzzles got harder, QE's performance dropped, while DF-AD stayed steady. It's like having a teammate who's reliable no matter how chaotic the game gets. Now let's switch frameworks to BAF. Suddenly, things got trickier for both methods. DF-AD still held up better than QE, but even it struggled with the most complex puzzles, dropping from near-perfect scores to around 90%. QE. It barely made it through half the toughest challenges. The researchers even found that random starting points, like flipping a coin to begin, made things more unpredictable. It helped QE in some cases, but created more ups and downs overall. Why does this matter? Well, think of BSAF as a well-organized toolbox and BAF as a cluttered garage. When the problem is simple, both might work, but when it gets complex, the organized system, BSAF, wins every time. DF-AD consistency under BSAF shows why it's a safer choice for real-world applications where reliability is key. So what's the big lesson here? Simplicity and structure matter. Whether you're building AI or solving a tough problem, having a reliable framework can make all the difference. And remember, sometimes the most consistent approach isn't the fastest, but it's the one you can count on when the stakes are high. Thanks for watching. If you want to see how these methods stack up in real-world scenarios, hit that subscribe button. And drop a comment. What's a puzzle or problem you'd like to see solved with AI?